Hello, what's going on here? It's the physics video lecture. This is the Graaff Generator. I was trying to demonstrate electricity, in particular lightning. Okay, let's see if we can turn this thing off. Discharge it one more time. Good, it's the physics video lecture, Psci 168, video lecture 33. We're ready to start talking about electricity and magnetism. This is our last major topic in which we hopefully tie everything together that we've done so far. This is called a Van de Graaff generator. I did see that we're getting some considerable sparks. Whoa, it's not totally discharged. There we go. Sparks from one to the other. That is lightning, as it were. And we're going to build the subject up from scratch. But what we have here was electric charge, and we had a discharge from that pole. So I'll turn these off to the side here. We are now talking about electricity and magnetism. Now, I've mentioned it often enough because we know we get our power, say, from the hydroelectric power plant. We need electricity and magnetism to get that power to do what we want it to do. So we're going to have to talk about electric motors, power transmission, everything. Good, so electricity and magnetism. But this does start with some new phenomena, and I'll just go ahead and start off that we had the demonstration of what's called the Van de Graaff generator. So you may want to look this up and get some images of the Van de Graaff generator. By way of friction, it gets electric charge on one side, and I have to explain this electric charge for a moment. So we now need to understand what is electric charge. We'll be talking about what's called static electricity. This is something that is actually going to involve a new fundamental quantity, but at the moment we just have some phenomena. And I'll start by showing that you can, here we'll take this one, you can rub a piece of plastic, and here let's get this thing discharged. You can rub a piece of plastic and you can think of the static electricity that you get when you pull clothes out of the dryer, for instance. So there's just some interaction. You saw that needle move here. Let's try another one. So this is just, I get a little better result here. So apparently there's a force involved because what? That needle's moving. Okay. And we can have a little more here. Now the explanation for the needle moving is that the same electric charge is on the black vertical part as on the needle itself. So there's actually a repulsion. But I'll have to demonstrate that a little more. For the moment, we're seeing some unknown phenomenon. It's associated with the same sparks that we had over there. So let me send this over here and do something related so I can generate some phenomenon on one side of this rod. It was that side right there. Now if I do that here, what I'm getting is a repulsion. So I have charge on the end of both of these clear plastic pipes, okay, plastic rods, and I'm getting a repulsion. You see, I can chase this thing around. And again, if you're exerting a force on something, there's an interaction. Okay. So that end, let's see when it comes to a stop. This end is the side that's, oops, stop that again, is charged. Okay, so that end is charged, regardless of what it does. Now I'm going to charge this plastic rod, and instead of chasing it around, it gets a stronger attraction. Okay, and I can reverse the direction because I'm going to attract to this side. So there are attractive and repulsive forces. Okay, so that's what we're going to see. I can catch up with it, and now it's going to, there's an attraction. Okay, other direction, there's an attraction. So we have attractive and repulsive forces. So without having seen any of these little so-called electric charges, we're going to name them positive and negative electric charge. So electric charge, positive, and then we just, call it plus, and negative, which we call minus electric charge. Okay, positive and negative. In fact, these names or designations were given by Benjamin Franklin, so it's a couple hundred years ago. Good, so we have the electric charge, and there is an interaction. When I say interaction, I just mean there was a force, and I demonstrated the force right here. So the interaction is that the like charges repel and the unlike charges attract. So interaction, which is to say force, and the law is that the like charges repel and the unlike charges attract. So I'll demonstrate that in a minute. Repulsion and attraction. So my examples would be this. Say I have a positive and a positive. They're going to be repelled from each other. Okay. If I have a positive and a negative, they are going to be attracted, which I'll draw with force arrows towards each other. Okay. And a negative will also be repelled. So that's the idea. Maybe I'll go ahead and draw that in between. So this one would be a negative and a negative that would also repel each other. Positive and a negative attract. Okay. And what else? I will put here, this really goes with part 2. Fundamentally, we say the electron carries a negative charge. So you may have heard this in chemistry or some other class. Electron carries a negative charge, and the proton carries the positive charge. Okay. So you got the electron and the proton. Fundamentally, we're never going to see those individually in this class. They're subatomic particles, so-called, very small. But yeah, the electron carries the negative charge, proton carries the positive charge. The electric current that we'll be talking about, say in a wire, well, I brought one wire to class, say in a length of wire, that will be the motion of electrons, typically. Good. So we got electric charge, the interaction, like charges, unlike charges, and those examples. Okay, so what are we going to do next? Keep numbering. Now with this little device, you actually saw that it's storing some charge in there because that needle has stayed put. If I discharge it, I've gotten rid of the charge in there, okay? So charge can be stored. And this demonstration object here is what I'm going to use for the idea conceptually. So we have just these two steel plates, and if we wanted, we could hook wires up to them, and they're just separated. Okay, steel plates separated by a certain distance, and the idea is we could say generate the negative charge and put them on one side, as we did with that device, and we take the other charge generation, the positive, and we put it on the other side there. I'm going to draw a picture of that. 4 or 5. So the next thing, we'll go ahead and erase all of this. We're going to talk about charge separation. Okay, so charge separation. And instead of those round plates, I think I can draw square ones a bit better. Okay. But yeah, we have two plates, two metal plates. They're separated by some small distance, and we have charge on one side and charge on the other. So that's going to be the idea here. Let's go ahead and imagine we have a bunch of positive charge. I'll put little pluses here. We have positive charge on one side and negative charge on the other. Okay. Positive on one side, negative on the other. Therefore, charge has been separated. So we could say on this side we have plus Q. So we're using the letter Q for charge. We've used it for heat in the past, but now it's charge. And on this side we have minus Q. Charge is separated. We just learned that these charges have an interaction. So if I have plus on one side and minus on the other, just as in these things, there's an attractive force. Okay, so I'm actually having to hold them apart. And in fact, we're about to talk about energy. It goes that quickly. So I have an attractive force here. What if I try to pull them apart? Attractive force, pull them apart. I've done work, and therefore there's stored energy. So already from that idea that we have a charge separation, we have charge separation and a force and interaction, and we immediately arrive at the idea that the separated charges can represent work, and therefore they can represent stored energy. Charge separation, here's what I'll write. Charge separation, force times distance, separation distance equals work. And that already tells us that separated electric charge represents stored energy. Okay. That's an E. So this implication, separated charge represents energy. There's energy in there, and we want to use that energy, for example, to power a light bulb. Now, in order for that to happen, we would have to connect this and let the charges flow. So charges can flow along what's called a conductor. So next, charge can flow along a conductor. Charge can flow along an electric conductor, and that's going to give us the idea of electric current. And I'm going to complete this little drawing before we come back and become really specific about these things. So we'll have an electric current, and we're going to use the letter I for it. I'm going to put a switch here. And here I'm just going to draw a light bulb for the moment. There's a light bulb. How about a little color here? Wait, so all these things have to be explained a bit more, but I'm kind of telling you where we're headed. So if I close that switch, charge flow, current flows. Now I just said that it would be the electrons moving, but the formal current is going to be from plus to minus. Okay. So we get a current that flows, and at the point where these two plates are neutral, the activity has ceased. So current has flowed, the light bulb glowed for a moment, and when these two are neutral, there's no more charge separation, therefore there's no more energy stored, and that energy was then radiated out by the light bulb. So that's the process of electric energy, and we're going to have to go back and systematically build that up. You notice I'm not using a battery, I'm actually using what would be called a capacitor, because it's such a clear image of charge being separated, force times displacement, stored energy, okay? So let's take these things one at a time. Now, let me label this separated charge. It's energy next. Charge can flow along a conductor, in electric current, and the electric current in the light bulb produces heat and light. And of course we know that heat is a form of energy, and that's where that stored energy went. So to complete this thought, electric current, so current flows through the light bulb. That produces heat and light. Both of them represent energy, of course. And at the point where we'd say this object has been discharged, it no longer has any charge separation, then that energy has been turned into heat and light. Okay, so heat and light, energy, and then it's run down. So that's our electrical process. And it's really based on the static electricity, so the stuff that you feel, when you go across the carpet and then touch something and get a shock. That's the static electricity. You may even see the spark. Pull clothes out of the dryer, you see a little spark as well. Okay, so that's just the outline. Let's do this systematically now. So I'm going to go back to the discussion of charge and introduce the units. And these quantities here. Okay, so returning to the physical units, up until now and all the way through thermal physics, and even when we're talking about heat engines, wind energy, solar energy, we were always using mechanical units. So we've just had mechanics up to now, and the units were the kilogram, the meter, and the second. Okay, so mass, space, and time. Make sure we write that down. Kilogram, meter, second. Everything we did was built up out of kilograms, meters, and seconds. Force, energy, force, displacement, etc. So that took us all the way through thermal physics, took us through heat engines, took us through solar energy. Now we get to electricity and magnetism. Now it's interesting, the terms, they go together, although we're specifically talking about electric charge right now. Magnetism comes later, but I'm going to go ahead and write it down because there's only going to be this new quantity, the electric charge. So mechanics, kilograms, meters, and seconds. Electricity, we have electric charge. We'll use the letter Q. And the unit of electric charge, which as we know comes in positive and negative, the unit of electric charge is capital C, the coulomb. Okay. Unit of electric charge is the coulomb. So now what do we have? Kilograms, meters, seconds, coulombs. That's it. We're not going to add another one. Everything will now be made up out of these four. So we've got the electricity, and when we come back to magnetism, we're going to see some new phenomena, but we're not going to have to go beyond kilogram, meters, seconds, and coulombs. Okay. What about the electron and the proton? The electron charge, it gets the letter E equals, let's say minus E equals minus, well, let's do it this way. Electron charge is negative E, and this letter E is equal to 1.6 times 10 to the minus 19 coulomb. This has to be stressed. Compared to 1 coulomb, a single electron, 10 to the minus 19, very, very tiny. It means if you're bringing enough electricity into play to have a 1 entire coulomb, it's roughly 10 to the 19 particles. Okay. What that means is the discrete nature of electricity can often be ignored. There's so many of those little particles carrying charge that we can think of them as a fluid that's flowing. Right? So I had already talked about current flowing. So it's very important how small the individual electron charge is. The proton charge is the same. Proton charge is plus E. The electron charge is minus E, and there's the actual quantity. So yeah, now we have the unit, we have the coulomb, and our next topic is the current that's flowing. Actually, let's not do the current, let's do the stored electrical energy. So we're going to actually come back to this thing, and now we know there are quite a bit of negative charges on one side, and the positive charges on the other, you could say it's the lack of the negative. The negatives were stripped from one side and brought to the other, okay? So what's left is the residual positive charge. And typically, you've got the same amount, it's balanced, so the sum total is 0, but it just happens to have been separated. So let's go ahead and make up a little room here. The energy in separated charges. So I'll draw a picture. So next, energy of separated charge. So let's do the same picture we had before. We've got the plates, referred to as a parallel plate capacitor when you have it this way. But what we want is just to have the positives on one side and the negatives on the other. So I'll stress that by saying we've got plus Q on one side and negative Q on the other. We're not going to do anything with it for a moment. So we have separated charge. We already argued attraction, separation equals work. And that work, we use the letter W often, right? So is referred to as Q times delta V. So the energy is the charge times what? The voltage drop, or the voltage difference, or just simply the voltage. So charge and voltage. Okay. Well, everybody's heard of volts before. Different voltages on batteries, wall outlets, you name it. So we can actually talk about the units here. We do the square brackets, and you guys remember we want to get out what the units are. So the unit of Q is the coulomb, and the unit of delta V is the volt. Coulomb times the volt. Okay. So we're already on seemingly more familiar ground, the voltage. So if you take coulombs times volts, you get joules. Let's even remind ourselves. That's the joule. So the joule is the coulomb times the volt. Important formula right here. So that was the energy of the separated charge. Now, remember I said we connected this to a light bulb, and the light bulb glows, and it's radiating power away. So how do we get from energy to power? Okay. This is the energy that's stored in the separated charge. How do we get to power? You'll remember, power is energy or work per time, energy per time. So I'm going to erase this and now write down the power formula. And what we're going to see is something interesting, because of course we've studied power formulas in the past. And this one's going to look very similar. We have the energy of the separated charge. So I've got room here. And I'll refer back to the picture where I have the wires connected in the light bulb. Electric current. So electric current, it's the letter I. It's just charge per time. Okay. The idea is it's flowing, say, along a wire. Here, I'll draw a wire. Okay. We've got charge flowing along a wire, electric charge, and a certain amount of charge crosses per second. So the units are coulomb per second, and the coulomb per second has a name. It's called the ampere. Equals ampere. So yeah, you could say 1 coulomb flows along the wire in 1 second, and that would be 1 ampere. So current, charge per time flowing past some point, okay, along the wire, and it's a coulomb per second is an ampere. Good, so now I can talk about the power explicitly and make a little room here. this we will call electric power. So we have energy is Q delta V, so it's the charge times the voltage, which represents the separated charge, the separation. So that's energy. And then power, we have P is equal to W over T, and we're going to go ahead and put parentheses around the Q over T times delta V, because this is going to be very familiar. The power is equal to the current times delta V, or P equal to I times delta V. And you can even put the units in here, and you'll actually never forget this. So we have watts equals amperes times volts, okay? And this is already a formula that you can use around the household electricity, okay? So let's even write that here. Watts equals amperes, or amps for short, times volts. Okay. Now, I left half the board free, and it's kind of nice to do a side-by-side here, because we've discussed power before in terms of hydropower. So let's remind ourselves of our hydropower formula. Back when we were studying hydropower, we had for the energy, we said it was M times G times H, because we were thinking of a reservoir, and it was above this power plant here. And as you guys will remember, we had a mass of water, and we had a dam here, and it was elevated, and there was the power plant, and so that was how much energy was stored in the lake. So let's do our power formula. And you'll remember it was M over T times G times H. So that's a direct analogy. What do we have here? Q over T, that's the current, times the voltage. Here we have M over T, that's the flow rate. And we never gave it another letter. We could have given it a letter, okay? In electricity we do. We call it the current I. But you've got a flow rate here, you've got a flow rate there, right? The current, the flow rate in water. This, of course, is joules per second. This is kilograms per second. But because of this analogy, we can see that G times H plays the role of a voltage. It's called a potential. And we even call this the potential drop. And in the analogy to our hydropower expressions, G is just a fixed number, gravitational acceleration, but H is the height of the drop here as well. So that analogy is pretty good, actually. So a high voltage corresponds to a high cliff here, so to speak. Okay. And a large current, Q over T or I, corresponds to a large flow rate. So yeah, we have a correspondence, we have an analogy between, or a correspondence actually, electrical power and hydropower. And of course, this is a mechanical power, so I'll just say mechanical power. Individually, these expressions are different. The left side, though, this is watts, and of course over here, this is watts as well. going to consult the clock. This is a good... Yeah, we're not going to do too much more. You know, we could never make this much progress. We could never go as rapidly as we have if we hadn't already studied energy so thoroughly. Okay, that's why we're able to pick up with these formulas here, show the analogy, and we're already talking about household wiring. I'll give one more, I'll give a couple examples of this, and then we'll call it a day. So I'm going to go ahead and leave this up. This hydropower analogy is extremely good from the standpoint of what we've been studying. So I just want to give some examples for the power formula. Examples of the power formula. So one of these would be car headlights. Car battery and headlights. So car battery delta V equals 12 volts. Car headlights, at least until recently, LEDs use a lot less energy, but we need to first talk about incandescent bulbs. So I'm just going to write here incandescent. So car headlights power could be, say, 60 watts for one or both. Okay, 60 watts for a car headlight. So what about our power formula here? So from P equals I delta V, we solve for the current, right? The current, we're just dividing both sides by delta V. We have P divided by delta V. So 60 watts divided by 12 volts would be 5 amperes. So that's an example of a realistic current, 5 amperes, which would be 5 coulombs per second. And I don't have it written down anymore, but that 10 to the 19, roughly 10 to the 19 electrons. So 5 times that number of electrons every second passing, you know, through, say, the light bulb, okay, through the circuit. Good, there's an example. You can make up as many examples as you want. You can in fact go to your household appliances. In the case of your household appliances, the delta V is 120 volts, alternating voltage, but it doesn't matter in terms of our formula here. So your delta V is 120 in the household appliances, and then you can look up the wattage that they use and figure out how much current they use as well. We'll do that next time. Good, so yeah, let's leave it at that. We're already well into the subject, of electric power, electric energy. Okay, see you then.